Series converges absolutely, converges conditionally, or diverges. And we're in section 10.7, so it's either going to be the root test or the ratio test. I am inclined, there's no guarantee here, to use the ratio test. And the reason why is because of that 17 raised to the k power. We do the root. Did I say ratio test? I'm inclined to do the root test. Yeah, root test. Because the kth root will cancel out that kth exponent. All right? Let me write the problem up here. This is to the 2k. All right, now I got to rethink this because of those parentheses. Let me think here.
Plus, I think.
Let's try the root test and see where this goes. So we're going to do the rho equals the limit as k goes to infinity of the kth root of, can I just leave off absolute value? It's always going to be positive, right? If you put in 1 for k, you're going to have 17 minus 17 is 0 to the 2 power. That'll be 0. If you put in 2 for k, 17 squared, that's 289 times square root 2 minus. It's always going to be positive. Okay, see that? So, well, it's always going to be positive or 0. But absolute value of 0 is still 0. So, we don't need the absolute value. But 17 to the k, this is in parentheses, square root k minus 17, and all this is the 2k. I'm not sure where this is going to go because of those parentheses, but let's find out. So, this could be written as kth root of 17 to the k, square root k, minus 17 squared, and then all that to the k. Because when we have an exponent raised to an exponent, we multiply them. Now that kth root will cancel out that k. And we have a limit as k goes to infinity of 17 to the k square root k minus 17 squared.
I got K. You gotta have that.
I believe this is going to go to infinity. This is 17 to the k as k goes to infinity, that's going to infinity, right? Square root k, that's going to infinity. Subtracting a constant when you're talking about infinity doesn't do anything. And then we're squaring it. So, I believe we're going to go to infinity. Now, what does the root test say if it goes to infinity?
Diverges, I think. I
Forget it does. Does it say diverge?
So 10. 17, 10.7.
Okay, I have to double check. to make sure.
Yeah, I will, they will.
If it's greater, if rho is greater than one, including infinity, it diverges. So let's try C. Diverges absolutely. All right. Is that K the kth root of K, or is that 17 to the K?
We haven't,
You see what I'm asking?
turn on the screen.
Oh, yes.
Oh my God.
Is that 17 raised to the K power, or is that the kth root of K?
Good question. Learned that one yesterday.
I
Yeah,
treated it
that's
as if it was 17 to the K power, but it might be kth root of K.
Yeah.
Well, no, because see the two K's outside the parentheses? The root canceled out that K.
K to the K over 1? No, K to the 1 over K.
So 1 over K. Let's do it again, and let's treat it as if that K is in the index of the root, so it's kth root of K. Is that all right? Let's do it that way. I treated it as if it was 17 raised to the K. But let's take this K, and let's put it down here in the index, like that, and let's see what happens, okay?
That's
I
true.
don't see what I would have done wrong if it was an exponent on the 17.
Okay, so the first one you guys did.
I tried it as if that's an exponent to 17, and I got infinity. Now we're gonna try it as if it's an index for that root. Does that make sense? So then we're gonna have the kth root. Absolute value is not required. 17 kth root, this is in parentheses.
It's the whole thing. Under square root.
2k.
Oh, this camera is struggling.
What's wrong?
The whole thing is under square root, or is it
It's
just?
under the kth root.
I thought it was just.
No, that's the square root test. Or
Or the root
The
test,
root
it's the
test.
kth root, yes? All right. Now, I won't go through the steps, but that will cancel that k. We still have the square. So we have 17
God,
kth root of k minus 17 squared. And because that 2 is a constant, we can do this.
what is wrong with
Like this. And we can factor out a 17. And I'll take it even further. We can split this into two limits, one for that, one for that. So that's gonna be, and that 17 applies to both. So we're gonna have the kth root of k minus 17 times a limit of 1. All that squared. I'm doing all this so that we can isolate this guy, this limit of the kth root of k. notice this one. The limit as k goes to infinity of the kth root of k. I'm gonna do it in terms of x, and I'm gonna write it as the limit as x goes to infinity of x to the 1 over x. Okay? And why did I do that? Because we're gonna use, eventually maybe, we gotta use the natural log method. So we're gonna let y equal this, and then we're gonna do ln of y equals limit, I'm gonna put ln inside, ln of x to the 1 over x. Now we can use the property of logarithms and bring that down. Like that. And we can rewrite it as just ln x over x. Does L'Hopital's rule apply here? Is that infinity over infinity? Is that the form? So take the log, the derivative of top and bottom.
1 over x divided by 1? No.
Yep. Which is just
1 over
Yes.
x. Oh.
1 over x, which is 0. But what equals 0?
The
Natural log y equals 0,
natural
right?
y. Oh, yeah.
So ln y equals 0, which means e to the 0 equals y, or y equals 1. So that limit now equals 1, we just found out. This limit is 1. So we have 17 times the limit as k, well, that limit is 1, I'm sorry.
Yeah.
Times 1, that is that limit, minus 17 times the limit of 1 is 1, and all this is squared, that's 0. Now what does the root test say?
It converges.
Converges,
Because it equals-
absolutely, right? Yes, converges absolutely by the root test. Which means it converges in general. So let's go back up here. Well, that was the correct answer. Converges absolutely. All right?
Yeah.
So over here, we had f of x equals sine x, and we wanted to approximate sine x at x equals 1/6, correct? So here, f of x is sine x, a is the pi over 6. So because these are polynomials we're generating, we're going to use the variable p for polynomial. And because this is a linear approximation sitting right here, we're going to call it p1 of x. That is replacing the y. Okay? Then, notice, to get this 1/2, we evaluated the original function at a. The original function at pi over 6, which over here is going to be a. So this will be f of a. That is like the 1/2 over there. Plus, then to get the slope, we found the derivative and evaluated the derivative at pi over 6. So over here, to do it in the general sense, we will evaluate the derivative at a. A is like the pi over 6. F prime of pi over 6 is like the square root 3 over 2 over there. Then we had x minus pi over 6 inside here. Pi over 6 is the x value for which we're evaluating it at. For this, it's going to be a, so it would be x minus a inside there. I'm going to take off with this. I'm going to find a p2 of x, which will give us all this with the x minus a squared. But are you okay with what this means?